The other mechanism for nucleophilic aromatic substitution is an elimination addition mechanism. So here, there's an elimination that happens first, followed by addition of the nucleophile. The requirements here are a little bit less than that of the addition elimination. The main difference is in the lack of electron withdrawing groups. So we still have a leaving group on the ring. So here that would be the chlorine or the bromine. We do need a hydrogen beta to that leaving group to eliminate. So as long as you have a hydrogen on a beta carbon, and remember that the carbon with the halogen would be your alpha carbon, and these would be beta carbons. And in this case, we have beta hydrogen on both of those carbons. Same thing on the structure below. And then in this case, you don't need any other electron withdrawing groups. So the reagent, again, is a nucleophile. Here it's OH minus. The heat is needed to help push this reaction along. So this reaction does require more forcing conditions. And that's because we don't have the electron withdrawing groups to help out. Forcing conditions is kind of an obscure term, but it just means maybe you're adding heat or pressure or something like that to help push the reaction. So the net result is typically pretty similar in that we're replacing the Cl. So here we would replace the Cl with an OH. In this bottom example, KNH2, our nucleophile is NH2 minus, so we're replacing the Br with the NH2. And with these, there's also a protic solvent involved. And we'll see why that is when we talk about the mechanism. So kind of the important thing to keep in mind here is how to differentiate this from addition elimination, the other mechanism, and essentially you just do that by the lack of the electron withdrawing groups on the ring. Before we talk about the mechanism, I want you to consider the following isotopic labeling experiment. And what that means is a certain atom was labeled with a specific isotope that could be tracked through the reaction. And in this case, the carbon where the halogen is attached was labeled as carbon-13, and KNH2 and NH3 were used, meaning NH2 minus is the nucleophile. And when this reaction was performed, an expected product resulted. So the product where the NH2 directly replaces the Br. But there was actually another product that came out of this reaction. And that product had the NH2 attached on the carbon next to the isotopically labeled carbon. So when this experiment was performed, it led researchers to ask the question, well, what is the mechanism? Because it's definitely not just a direct substitution at this labeled carbon. Something else must be going on for this nucleophile to be added next to it. So here's the proposed mechanism. We start with our aromatic ring with the Br. And I'll keep my red dot for the isotopic label. And we know that we have a beta hydrogen to the Br. So instead of the NH2 acting as a nucleophile in the first step, it instead acts as a base. So this is an elimination step. It grabs this proton. Those electrons fall down to give you a triple bond, and you lose Br as a leaving group. Here we get a very interesting and hotly debated structure that has since been accepted. This is called benzyne. And it's quite interesting because of the fact you end up with a triple bond in a six-membered ring. And we know that triple bonds are generally linear, so fitting that in a six-membered ring is quite rare. Well, this benzyne is highly electrophilic. From here, what happens is the addition part. So now NH2 that's floating around can act as a nucleophile. So I'm actually going to draw this twice because there's two different options. The NH2 can add to the isotopically labeled carbon, and that will push those pi electrons to the right as a lone pair. But it's equally likely to add to the other carbon. So it could add right here and push the electrons onto the isotopically labeled carbon as a lone pair. This shows us how the NH2 adds to the two different positions. Now we're not quite done yet, so this is where the proton source comes in, the NH3, and we just need to protonate the ring to get to the final product. So we'll use that lone pair and just pick up a proton. This gives us our first product, and then we can do the same thing with our other intermediate. And that gives us our second product. All right, here I just want to show you one example of predicting the products for this elimination addition reaction. And we have our aryl halide, which is a chloride. We have our strong nucleophile, NH2, along with the NH3. So look for beta hydrogen. The chlorine, we'll say that's on an alpha carbon. We have a beta carbon here and a beta carbon here. The one on the top, there's a methyl group there, so there's no hydrogen. But the one on the bottom, there is a hydrogen. Now there is one thing you want to do here to make this reaction a little easier to analyze. We want to draw the resonance structure of the aromatic ring where the double bond is between the beta hydrogen and the leaving group. So we want the one where the double bond is between the alpha and the beta carbon with the hydrogen. So to do that, we can just move these pi electrons around the ring and draw the other resonance structure. Now we're set up to do the elimination to get benzyne. So what I would do is just go ahead and draw the benzyne. So we're going to form it like this. And then from there, we can end up adding the nucleophile to either of these positions. So without going through the full mechanism, we can predict the products. We'll have one where an NH2 is here. Plus one where an NH2 is here. Right now, bear in mind that in this case, the beta hydrogen here did not exist. But if you had a beta hydrogen here, you could potentially get benzyne at this position and this position to add the nucleophile at 3 different locations. So just keep that in mind when analyzing a reaction.